Hello Year 12 and welcome to our first video here for projectile motion. Now when we talk about projectile motion, we're talking about some object, some projectile or particle that's launched into the air up and across and that then falls back to the ground under gravity. So we can describe the position of that particle at any particular point in time with coordinates x and y, right? Because it's going up and down and across. So using the coordinates x, y, or a position vector OP. Now, because my particle is moving in the vertical and horizontal dimensions, and they're changing over time, we've got three variables there, and that makes life a little bit difficult for us at this stage. So rather than deal with all three variables at once, we're going to break this up into vertical and horizontal components and look at those changing with respect to time. So some function that describes my horizontal displacement over time will be some function of t. X will be some function of t, and the vertical displacement will be some function of t also. These are our position equations. And if we look at how our position is changing with respect to time, we examine that position function a little further, we see how the position is changing with respect to time. We're looking at the velocity of that particle. So if I come up with a new function now that describes the velocity with respect to time, that will be the derivative of my displacement. Okay, so the derivative of the displacement is the velocity, or similarly, the integral of the velocity is the displacement in both x and y. Now, for a particle's velocity to change, it will need to accelerate, and to accelerate, it needs some force to act on it. Once we launch this particle into the air, there's only one force that's acting on it, and that's going to be gravity, which operates straight down, so it's negative, and probably negative 10 or negative 9.8. It'll be specified in any question that you do. But there's no horizontal force acting on our particle, which means the horizontal velocity can't change. So the horizontal velocity is a constant. The vertical velocity is changing. It's being affected by a constant force of gravity, which means that it's constantly changing, and in fact it's constantly decreasing. Describing the change in velocity is the acceleration of our particle. So x double dot, our horizontal acceleration, is equal to the derivative of our horizontal velocity. But we know, and I can't stress this enough, our horizontal velocity is constant, so our horizontal acceleration, when I differentiate a constant, is equal to 0. The integral of 0 is a constant. Our vertical acceleration is a constant. Our vertical velocity is changing at a constant rate. So we can see here, I think, we can see the parabolic path that our particle traces here, and we can probably watch that occur. Okay, up and down again. Now, if I just track the horizontal component, you can see that blue point there just moves steadily from, well, we're going to look from left to right. It moves across at a constant speed from start to finish. Constant horizontal velocity doesn't change. We can look at the same thing here. Now we're just going to observe the vertical component of our displacement, and from that we can sort of infer our velocity and our acceleration. So you'll notice it goes up and stops and comes down again. So our initial velocity is positive, and it's steadily decreasing until it becomes 0 and then becomes negative again. It goes up and down. That point where my vertical velocity is equal to 0, that's the highest point that my particle reaches. Okay, and that's an important thing to remember when we're solving some problems later on. The highest point our particle reaches is where the vertical velocity is 0. My horizontal velocity is the same throughout, but my vertical velocity begins positively, normally, becomes 0, and then becomes negative. Okay, moving along a little bit further, we can describe our velocity using vectors, either as these horizontal and vertical components, or we can look at those components as being the projection of the velocity, or the speed if you like, onto the horizontal and vertical unit vectors, I and j. But more commonly, we're going to describe the velocity with an angle of inclination. That's the angle between its direction and the horizontal. That's our angle of inclination, and a speed, which is a scalar quantity. How fast it's going and what direction it's moving in. That's how we are probably mostly going to describe the velocity at any point, particularly its initial velocity. So we can see here there's two vectors I've drawn onto the path of our particle there, our initial velocity with our initial angle of inclination, and some velocity at a time t with a different angle of inclination and a different magnitude of that vector as well. You can see that vector is somewhat shorter than the original one because the particle is moving slower at that point in time. I can break that vector up into its vertical and horizontal components, to its x and y velocity components. And hopefully you notice there that our x components have the same length at both points. They're both moving the same distance to the right because our horizontal velocity is constant. Our vertical velocity, you can see at these 2 points though, is significantly different. In the first case, it's large and positive, and in the second case, at time equals t, it's smaller and negative. Okay, horizontal remains constant, the vertical changes, and changes at a constant rate. So in our first example here, we're given, let's say, an initial velocity. This is probably how it's described, but some velocity of 12 meters per second at an angle of inclination of 60 degrees, and I want the horizontal and vertical components. Okay, we did some of this with vectors, and it's just right angle trigonometry that, given a hypotenuse of 12, to find the horizontal component, I'm going to use the cosine ratio. So 12 cos 60 is my horizontal, which is 6 meters per second. My vertical component is going to be 12 sine 60, which is 6 root 3 meters per second. Okay, and that gives us our horizontal and vertical components. That's an important first step in many problems. In our second example here, we're given a velocity vector, right, 5i minus 2j, and we're asked to find the speed and angle of inclination. So to find the magnitude of that vector, it's the square of the sum of the squares. Sorry, the root of the sum of the squares. So 5 squared plus negative 2 all squared gives us 29. The square root of that is root 29. So that's our speed, which is the scalar magnitude of our velocity. And then to find the angle, we're going to use inverse tan. We get negative 2 over 5, which gives us an angle of negative 22 degrees. It helps to have a diagram with those things because sometimes, as we'll see in a later example, whether we're traveling down or if we should happen, for whatever reason, to be measuring an angle in what we might think of as the second quadrant, tan will be negative there. Now, here's a much longer example, and this example will go for some time, so be prepared. So a ball is thrown with an initial speed of 40 meters per second and an angle of inclination of 30 degrees. So we've got speed and angle of inclination from the top of a stand 25 meters above the ground. We're going to use that point as the origin, which means the ground is 25 meters below the origin. We're told that g is to be negative 10 meters per second squared. That's our initial vertical acceleration, and in fact, it's the constant vertical acceleration is -10. We're asked firstly to find the 6 equations of motion. So we know that our horizontal acceleration equals 0, and this is the case for all of our questions in this unit. So our first equation is x double dot equals 0. We integrate that, and we find that it's some constant, but from our initial conditions there, of 40 meters per second, an angle of inclination of 30, we can determine that our initial horizontal velocity is 40 cos 30, which is 20 root 3 meters per second. And that's not just the initial, that's the constant, because when we integrated 0, we just got a constant. It's independent of time, our horizontal velocity. So 20 root 3 is the horizontal speed of this ball at all points in time, from start to finish. Now, to find the horizontal displacement, of course our horizontal displacement is changing all the time. The ball is moving across. So we integrate 20 root 3, and we get 20t root 3 plus some constant. However, we know that our initial horizontal displacement is 0. We said the launch point is our origin, or 0, 0. So given our initial displacement is 0, substituting t equals 0, x equals 0, we find our constant is also 0. So our third motion equation is x equals 20t root 3. So that's our 3 horizontal motion equations. Now we do something very similar with the vertical motion equations. The difference now is that instead of our acceleration equaling 0, in the vertical our acceleration is equal to -10 as provided in the question. So I integrate that and I get -10t plus some constant. And again, from our initial conditions, we know that our initial vertical velocity, right, is 40 sine 30, which is 20 meters per second. So substituting in t equals 0 and y dot equals 0, we find that our constant is equal to 20. So our second vertical motion equation is y dot equals -10t plus 20. That's 2 of our 3. To find the vertical displacement, we have to integrate our velocity. The integral of -10t plus 20 is -5t squared plus 20t plus some constant. We notice now it's a quadratic, and that we will produce 2 solutions. The ball goes up and down again. So we've got that quadratic. Again, from our question, we're told that our launch point on top of the stand is the origin. So that means at t equals 0, y equals 0, substituting those things in, we find that c also equals 0 in this case, our constant there. So that gives us our 6th and final motion equation, y equals -5t squared plus 20t. There's our 3 vertical motion equations. That's part A done. We found our 6 equations. You'll need to derive those each time. When I say derive, I mean compose those, not necessarily by differentiating. You'll need to find those 6 equations for most questions. Now, there is, of course, a part B. We need to find how high that ball rises, how long it takes to get to that maximum height, what the speed is then, remembering speed is a scalar, and how far horizontally it is from the stand at that high point. Now, if we remember earlier in the video, I mentioned that the highest point is where our vertical velocity changes from positive to negative, right? Where our vertical velocity equals 0. So we let y dot equal 0. Substituting that into our vertical velocity equation, we solve for t, and we find that t equals 2 seconds. So 2 seconds after the ball is thrown, it reaches its highest point. That's sort of the second part of this question. But to find how high it is at that point in time, I have a function that describes the height of the ball with respect to time. That's my vertical displacement equation. So substituting t into that equation, we find that my vertical displacement is equal to 20 meters. 20 meters above the stand, and I guess we could say 45 meters above the ground. So after 2 seconds, the ball has reached a maximum height of 20 meters above the stand. So that's two parts of the question. I need to know its speed at that point and how far horizontally it is from the stand. Now, at the maximum point, it has no vertical velocity, right? The vertical velocity is 0, and the horizontal velocity we know is a constant. So there's really no calculation to be done for this part here. My horizontal velocity is a constant for this question, 20 root 3 meters per second. There's no vertical component. So at the maximum height the ball reaches, 20 meters above the stand after 2 seconds, the ball is traveling at 20 root 3 meters per second, a speed of 20 root 3 meters per second. Its direction is horizontal. Now, to find how far horizontally the ball is from the stand, it's 20 meters above the stand. How far across from the stand is it? Again, I have a function that describes horizontal displacement with respect to time. That's my horizontal displacement equation. Substitute t equals 2 into that equation, and we find that my horizontal displacement, x, is equal to 40 root 3 meters. So the ball has gone up 20 across 40 root 3 in 2 seconds. And after that point, it will start coming back down again. Rightio. So that's part B done. That's not the end of the question though. There is a part C here as well. We're asked to find the flight time, the horizontal range, and the impact speed and angle. So the ball has gone from the top of the stand up another 20 meters. Now it's going to fall 45 meters from there. It's going to come down until it is 25 meters below the top of the stand, which is at ground level. So I need to solve my vertical displacement equals negative 25. That's going to give me a time. As a matter of fact, it's going to give me 2 times, but we'll sort that out in a moment. The horizontal range is going to be how far the ball has traveled horizontally in that period of time. Okay, so we're going to find t by letting y equal negative 25. Then we're going to substitute that t into my horizontal displacement. Will give me my horizontal range. To find the impact, speed, and angle, we'll substitute the time into our vertical and horizontal velocities. Find the magnitude of that vector there, and also find the angle of inclination. So let's work through this. Our flight time is when y equals, or our impact, our time of impact is at y equals negative 25. Substituting into vertical displacement equation, we get this quadratic. Divide throughout by 5, and then factorize, and that tells me that t equals negative 1 or 5. Now t equals negative 1 doesn't make a lot of sense. That's before the ball was thrown. So we can discount that solution, and we're only after the t equals 5. So the ball will hit the ground 5 seconds after it's thrown. Given that the ball will hit the ground 5 seconds after it's thrown, and knowing that the ball travels across horizontally at a constant 20 root 3 meters per second, right, substituting t equals 5 into our velocity equation, we find the horizontal range is 100 root 3 meters. So after 5 seconds, the ball has traveled across 100 root 3 meters and then hit the ground. So now for the impact, speed, and angle, I need the velocities, vertical and horizontal velocities. I kind of already know the horizontal velocity. But the vertical velocity at that point in time, substituting t equals 5, tells us that the ball is traveling down at 30 meters per second. It's traveling across at 20 root 3 meters per second. So we square those two values, add them, and take the square root, and gives the impact speed at 10 root 21 meters per second. To find the angle, it's the inverse tan of our rise over run. So 30 or negative 30 over 20 root 3. Now this is going to give us an answer of negative 41 degrees. But a diagram is going to explain to us why we don't want a negative answer. Okay, we're not after a fourth quadrant solution, and I'm not after a second quadrant solution either. Now really what we're talking about, because the ball has travelled across and down, the angle of inclination I'm going to be measuring on the left hand side of the angle, if that makes some sense. Okay, we'll have a look here. So I'm really after this angle here, but when we do the inverse tan, it gives me the angle from the positive x-axis. Okay, so I need to make that adjustment, and instead of being negative 41, it's 41 degrees. So the little diagram here that shows us what's happening here, here's my 25-meter stand that the ball is launched from at 40 meters per second at an angle of inclination of 30 degrees. There's a little, here we go. We should see the ball travel up. At 2 seconds it reaches a peak, then comes down the 20 and the extra 25 meters and impacts the ground at an angle of 41 degrees. And, oops, oh, we've got that again. In a moment. So, my 6 equations of motion. We're just summarizing all of our results here. There's my 3 horizontal and 3 vertical equations of motion. Then I have the maximum height of 20 meters after 2 seconds, at which point it has a speed of 20 root 3 meters per second and has traveled across 40 root 3 meters. Finally, the flight time is 5 seconds. The horizontal range is 100 root 3 meters, and the ball impacts the ground at an angle of 41 degrees and a speed of 10 root 21 meters per second. Okay, you can see that's a fairly long, involved question there, but most of the time it involves us finding the time and substituting that into either our velocity or displacement equations. Rightio, that's it for the first part of 10A. There's more to come. So hold tight. If you've got any questions about this, make sure to let me know. But I hope it makes sense to you. Okay, cheers.